Hey guys, welcome to lesson 8.2, where we look at hypothesis testing, p-values, and making decisions. All right, so in lesson 8.1, we looked at potentially Alex being accused of cheating, and the presumption is, with anyone taking an exam, is they took it honestly and didn't cheat. But if we suspect that someone cheated, then we're going to present the evidence and kind of weigh the evidence. So the presumption stands unless evidence overturns it. So if the evidence is not sufficient, then there's not enough evidence to conclude that someone cheated. The panel hears the evidence. There's going to be 3 exhibits. And there's always a possible explanation for things that happen. We just want to look at the preponderance of the evidence. So first of all, the first 5 exams, the class averaged an 88 and Alex averaged a 74. Alex also never scored above an 85. On the final exam, the class average dropped from an 88 to an 82. So the class went down from 88 to an 82, but Alex jumped up from 74 to 97. He also got a perfect score on the 5 questions where the class averaged 30. So class went down, Alex went up 23 points. Now, Alex could have slacked all semester, gotten his stuff together, and there are legitimate situations in which a student steps up their game and just excels. We don't know what else could have happened. So that in and of itself is certainly not evidence of cheating, but it is absolutely a red flag. That's something that I think should be looked at more closely. Second of all, the pace. Through the first 5 exams, Alex averaged 52 minutes per exam. He completed this one in 22 minutes, whereas the rest of the class averaged just over an hour, so 61 minutes. So all 35 questions, Alex had never finished before in under 45 minutes. So now Alex is doing exceptionally well in terms of correctness, and he's also finishing at an extraordinary pace compared to his previous attempts and compared to the class. So being able to finish an exam very quickly, very correctly is a huge red flag for some sort of dishonesty. But again, we could say it's not out of the realm of possibility that someone did really well, really quickly. So finally, we can look at the camera setup. So for 22 out of the exam's 22 minutes, this is what we saw. Workspace, there's nothing below the neck was visible, and this frame is representative. So pretty much for 20 out of the 22 minutes, this is what the webcam camera shows. Now, sometimes a camera like flips up, and that can happen, but given the pace, given the instructions for how the camera should have looked, given the correctness, all of that really, makes us suspect. So the question is like, is he, looking down all the time? Could be looking down at his notes, but could also be looking at his phone. So the test statistic is all the evidence summarized. No single exhibit convicts. Each one has a possible explanation, but all of it together, the question is, does that point to cheating or does it not point to cheating? The test condenses the entire sample into one standardized number. Now, the idea is like, how likely is all this if someone did not cheat? So that's what the p-value is. We'll work with p-values throughout the pretty much the rest of the year, rest of the lessons. When I say year, I mean, we've got the rest of the course. So if Alex is honestly a 74 average student, how likely are these results, or more extreme? By more extreme is instead of getting 97, he got 100, or instead of finishing in 22 minutes, he finished in like 10 minutes, right? So, getting 100 finishing in 5 minutes would be like an extreme result. So the p-value is a probability. That's one thing you have to understand. So the p-value is a probability. Oops. That we have a data that's as extreme as we've observed if the null is true. So if Alex did not cheat, that's the null hypothesis, how likely are these three pieces of evidence? So the 97 finishing in 22 minutes and the webcam basically just showing the nose and up. Small p-value, data like ours almost never happens if null is true, is strong evidence against the null hypothesis. And one second. A large p-value. So large p-values, it's all relative, but pretty much a small p-value is often going to be something less than 0.05, so less than 5%. Large p-values, it's all going to be dependent on this thing called alpha, but the idea is, if our p-value is like 0.2, 20%, that's going to be considered a large p-value. As extreme or more extreme. So here we have a p-value. It's a probability, so we're going to be using the z curve and the t curve in the next couple of sections to compute p-values. And p-values are going to be areas. It's either going to be in one tail or potentially it's going to be in two tails, but we'll go into like the exact mathematics of that in the next couple of sections. So how likely is it that Alex got a 97 if he is a 70% student historically? How likely is that student to get a 34 out of 35 correct? And we can throw in like other pieces of evidence, like being able to finish very quickly, et cetera, et cetera, et cetera. So we have a pretty low p-value on that. So the probability that Alex did this without cheating is like 1 in 2,800. So the p-value is not the probability that the null hypothesis is true. It's the probability that it's true given our data. So it's not the probability that he's innocent. It's the probability that he's innocent given the three pieces of evidence that we've seen. So make a decision with alpha. Alpha is called the significance level, and you establish that beforehand. So for example, for the decision board at Virginia Tech, it's they have to, I think for them, the standard of proof is more likely than not. So if it's reasonable that there's more than a 50% chance that someone cheated, they are instructed to side with the instructors. But like for me, if I'm writing a student up, for me, it's like I have to be like 98% confident that they cheated before I present any sort of evidence. So for me, the bar is pretty high, and I think it should be. So if the p-value is less than or equal to alpha, we reject the null, and we say there's enough evidence to conclude the alternate. So the ruling would be in violation if the p-value is small. If the p-value is bigger than alpha, then we say there's not enough evidence to conclude the alternate, and the presumption survives. So he is innocent until proven guilty. Now, you can have two types of errors that can happen. You can have type 1 and type 2 errors. So there is the reality, and then there's the decision. So in reality, if Alex did not cheat and we don't find enough evidence of him cheating, this is the correct decision. Now, if he cheated and we find that there is enough evidence to conclude that he cheated, that's a correct decision as well. Now, we can have an error, right? So in reality, if Alex did not cheat, but we convict him of cheating, that's a type of error. So a honest student is punished. That's a type 1 error. In reality, if he did cheat and we don't find that there's enough evidence, again, that's a type 2 error. A cheater is cleared. So type 1 is a false positive. A type 2 is a false negative. The probability, so there's one more term, it's called power. And power is the probability that a real cheater gets caught. So a couple things can influence power. More evidence. So if you have a 10-question quiz versus a 35-question final, here there's going to be a bigger sample size, and so doing well on like a 10-question quiz versus doing really well on a 35-question final, there's going to be more evidence when you have a bigger sample size. So sample size influences power. Brazen violation. So going from a 74 to a 97 is a lot harder to explain than going from a 74 to a 79. So the effect of the size makes a difference. And looser standard of proof, bigger alpha catches more cheaters, but it also means that you punish more honest students. So for example, if for me, like internally, I have to be like 98% confident that a student cheated before I write him up. But if I just like sort of kind of believed it, right? If it's like, well, it's more likely than not, so 50-50, then I would be turning in, potentially a lot more students that didn't cheat. Now, they would still go through the panel, but the looser standard of proof is something that can affect. But in that situation, I would also be writing up more actual cheaters. So power is why not in violation never means proven honest. Weak tests let real cheaters through routinely. So let's look at a couple of examples. A test produces a p-value of 0.08 with a alpha of 0.05. State the statistical decision. So the decision would be reject the null hypothesis, and the honor court ruling that corresponds to it. So we would say there is enough evidence to conclude that the alternate is true. So in this case, Alex cheated. Delivering the ruling, a different test produces a p-value of 0.19. State the decision. So we would fail to reject the null hypothesis. We would say there is not enough evidence to conclude that Alex cheated. So in that situation, we would say, all right, this p-value means that the odds of seeing that sort of evidence against Alex, if Alex in fact is honest, are about 20%. And that means that like 1 out of 5 times, this can happen just by chance. And that's like, to me, not enough to write someone up for cheating, where the stakes can be relatively high. Name the errors. In Alex's hearing, describe a type 1 error and a type 2 error in plain language. So type 1. Let's go back and take a look at them. So in a type 1 error, so Alex is honest. Alex didn't cheat. So the null is true. He did not cheat. And we made an error. But he got written up, written up by the panel. So they made an error. In type 2, Alex did cheat. So the alternate hypothesis is true. But there was not enough evidence to write him up. Not enough evidence to write him up. So in both situations, there is an error. In type 1, the null is true, but the null is true, but we conclude that it's not. In the type 2 error, the alternate is true, but we don't have enough evidence to conclude that. So classic misreading, exhibit 1, the p-value is 0.0004. A classmate says there's a 0.4% chance that Alex is innocent. Explain the error in one of the two sentences. It's not that that's the percentage that Alex is innocent. That's the percentage that we have the evidence that we have if Alex is innocent. So vocab test statistic, it's a standardized number, how far the sample landed from what the null predicted. P-value, it's a probability, if the null is true, that we have the sort of sample that we do. Significance level is the pre-chosen cutoff for rejecting the null. Statistically significant means that the probability is less than alpha. Fail to reject the null, insufficient evidence. A type 1 error, rejecting a true null hypothesis. Type 2 error, failing to reject a false null hypothesis. And power is the probability. Power is a probability of correctly rejecting a false null hypothesis. So a couple summary things. Power is the probability that we catch real cheaters. It goes up with more evidence. It goes up with kind of more brazen evidence. And it goes up with looser standards for writing someone up. So if we have a looser standard of writing someone up, we will catch more cheaters, but that also means that we're going to incorrectly write up more people that didn't cheat. So it's just kind of a double-edged sword. Test statistic condenses all the evidence into a single number, and a p-value tells you how likely is that number if the null hypothesis is true. The decision, once we have a p-value, is based on a fixed alpha. If p is less than alpha, we reject the null. If p is greater than alpha, we fail to reject the null. Type 1 errors punish the honest. Type 2 clears the guilty. And yeah, you're just gonna have to be able to recognize and articulate what the two types of errors are. So that's lesson 8.2. In the next couple of lessons, we're actually gonna look at the mechanics of finding p-values from different test statistics, and we're gonna practice this idea of like rejecting the null, failing to reject the null, and articulating what that means in words.